Hello, welcome to my second video in our Gen Chem series. And today we're going to be talking about electron orbitals and electron configurations. So in the last video, we kind of just did a quick review of the structure of an atom and the subatomic particles. And we talked about how electrons are found in shells and orbitals. And we looked at the different kind of types of orbitals. So let's start there today. So remember that the kind of golden rule of an electron orbital, a rule that is never broken, is that electrons can live in up to a pair per orbital. So that's one pair of electrons per orbital. And remember, when I say the word orbital, means one specific thing in this diagram. So for example, the s orbital, or the kind of like the s flavor of orbitals, really only comes in one type, right? There's just one way to make a sphere. So the s orbital, there's only one of them. But the p orbitals and the d orbitals, you can see there's actually many different ones. And the main difference is kind of the direction that the shape of the orbital is facing. So in the dumbbells of the p orbitals, like the px orbital right here, that px orbital is kind of aligned with the x-axis. So I kind of think of it as the horizontal p orbital. So each one of these can hold up to 2 electrons. So I also said in the last video that I wasn't a big fan of kind of this drawing of carbon. This is kind of the prototypical way that an atom might be drawn, especially like the first time you've ever seen kind of an atom be drawn out, like in Gen Chem or even high school chem. And this drawing is showing the electron shell. And so one of the questions I kind of want you to be keeping in the back of your mind as you watch this is, what is the difference between an electron shell and an electron orbital? So that being said, I kind of want to show you a different representation of a carbon atom here. So let's scroll down. And this time I want to put carbon's 6 electrons in their actual proper orbitals. So not their shells and their proper orbitals. So remember, we're going to kind of be adding these kind of as pairs. So the first 2 electrons actually go in an s orbital. So the very first orbital is an s orbital. And this is true for every atom, right? So if I were to stop here, this would kind of look like a helium's atoms, electrons. And um, this means that the lowest energy orbital overall is this first s orbital. So this is our s orbital. And just as a reminder, it's the lowest in energy because it's the closest to the nucleus. So those electrons are really happy. They're really glad to be so close to those protons and like really feeling the attractive force between them. And remember, as we add energy to electrons, we go further away from the nucleus because it takes energy to go further. And so the second orbital, it turns out, is also an s orbital. So this next orbital is it's called the 2s orbital. So here is our 2s orbital, right? So we've put the first 4 electrons in, and now we're going to actually finally get to the next orbital type. So we're going to do the p orbitals. So let's draw that in here. Okay, so horizontal one, this one's going to be kind of our px orbital. Our vertical is going to be py, and then we'll say this depth orbital is our pz. And the thing to know about these p orbitals is they're all equivalent in energy. And hopefully that kind of makes sense, like from a physical kind of intuition standpoint, right? Because energy of the orbital is really how far away it is from the nucleus. And so since they're all the exact same like shape and size, I'm just pointing in different directions, they're going to have the same energy levels. So the fancy kind of technical chemistry term for that is that these orbitals are degenerate. So the p orbitals are degenerate, which is that they are equal in energy. Okay, and so that means with these final 2 electrons, I can put them in any of the 3 orbitals that I like. And one thing I want you to think about really quickly is, am I going to put them both in the same orbital? So am I going to put a pair of electrons, let's say in the px orbital, or would I rather put one in a px and then let's say one in the py orbital? Which one do you think seems more realistic? The answer to this is it's going to be more realistic to put them in separate ones, because remember, electrons are both negative. They repel each other. They don't want to be near each other if they can help it. So they're actually going to try and be kind of or like kind of orbiting in different directions if they can. Okay, so we're going to put the last two carbon electrons in a px and a py. So let's say I, for the future, didn't really want to write all of this out. Let's say I was doing a bigger atom or just had to do this a lot, and I wanted some kind of notation, some shorthand to do this. So we could say, okay, I've got an s orbital. Let's call it like the first s orbital. So the 1s orbital. And then I've got the 2s orbital for carbon. And then I also use my px orbital and my py orbital. And then I'm going to put how many electrons went into each. So I put 2 in the s's, and then I put 1 in the x and 1 in the y. And just to be complete, let's write the pz and write a little 0, because we do have that pz orbital here. It's just empty right now. But we could have just as well put an electron there. And as it turns out, this is what essentially what an electron configuration is. It's just like a conversion of this kind of diagram, like this more accurate and kind of nuanced version of an atom that really shows you where the electrons are, and you're condensing that information into a shorthand. So this is an electron configuration. So this is kind of the perfect segue to start talking about something called quantum numbers. And maybe that's ringing a bell from Gen Chem or maybe even high school chem, and it's ringing a bad bell. Maybe this is like something that at the time didn't really make much sense. I know that it definitely didn't make much sense to me. And anytime I hear the word quantum, my eyes start to kind of gloss over. But I want to kind of convince you in this video that they're really not too bad. I promise they're really not too bad. And in fact, they're kind of already baked into the electron configuration. So let me explain that. So quantum numbers, they're not really numbers at all. Well, I mean, they kind of are, but what I kind of rather think of them as is the set of four different qualities that each electron has. Four different qualities that each electron has. So let me move down our electron configuration from earlier. And so the first quantum number is actually called the principal quantum number. And so that's actually the numbers that kind of come before the orbitals. So the 1, actually, let me rewrite our electron configuration into kind of a more standard version. So the standard way you might kind of see it would look something like this. So it would look like 1s2, 2s2, 2p6. This would be carbon's electron configuration. Oh, whoops, sorry, not 2p6, 2p2. And so what happened here, really all that happened was we took the one that we made and condensed the 3p orbitals into kind of one. And that's just because they're degenerate, and so they're equal in energy. So kind of easier to just kind of view them as, well, they are 3 different orbitals, but it's kind of easier to just kind of write them as like one thing. Okay, and not write out the 3 each of the p orbitals. So that being said, the principal quantum number is actually the numbers. It's the 1, the 1s, and the 2s. So this is the kind of energy level, the energy level of the orbitals, roughly. So kind of what it's roughly saying is generally the orbitals that have the same principal quantum number are similar in terms of energy. They're not actually going to be exactly the same, and in general, like s orbitals are going to be a little more stable, a little less energetic than p, and p orbitals are going to be like a little more stable than d. But really, it's giving you kind of a ballpark number. And so, really, if we look at like the fact that we have two different s orbitals here, it's saying that the one s orbital, is lower in energy. So that's the principal quantum number. Um, and the second kind of quantum number is actually just kind of the flavor of the orbital. So it's just the fact that it's an s, a p, or a d. It's called the azimuthal quantum number, but yeah, you don't even need to know that. But really, it's just referring to the s's versus the d's and the p's. This is the second number. And then the third quality that's already baked into the electron configuration is actually kind of going back to our earlier version, which is telling us which specific orbital it's in, if it's in a p or a d orbital. So remember, p and d orbitals, there's actually many different orbitals in them. So saying which specific one it's in. Is it in the x, the y, or the z, or so on? So that's kind of the final one. Or really, it's the third number. And it turns out that the last number is something called spin. So before I explain spin, let me bring up one other kind of important thing that I want you to know, which is called the Pauli exclusion principle. Which really just says that every electron in an atom is unique. So the technical definition, what it actually says technically, is that every electron has its own unique set of quantum numbers, which sort of makes sense. It already kind of looks like that's kind of naturally happening, right? You only have up to 2 electrons in each orbital. So for example, if we were to just look at the electron in the px orbital, there's no other electrons in the px orbital. And so it's got a completely unique set of quantum numbers. But as we know, you can put a pair of electrons in the orbitals, right? So if we did the same thing with the 2s orbital, well, that seems like that already broke our Pauli exclusion principle rule, because now we have 2 electrons, both are in the 2s orbital. So they have the same quantum numbers. And that's where the fourth and final kind of quality, the final quantum number comes in, which is something called spin. So spin is something that is way over my head. It is definitely some quantum mechanics stuff, but spin basically refers to electrons being either up or down. So like, are they spinning, I guess, up or down? And it's kind of the answer as to why everything in chemistry seems to be always pairs of electrons. It seems like we're always talking about pairs of electrons and never really one electron. Sometimes we do, but usually it's pairs. And this is the reason, is because we always have a pair of electron orbitals, because we can always have an up and a down electron in the orbital. And so maybe from Gen Chem, you remember kind of doing something that looks like this with like the orbital energy level diagrams and like filling these up and writing the up and down arrows. And so those up and down arrows are referring to the spin. Yep, so we could even kind of amend our diagram here and show that the 2 electrons in the 1 and the 2s orbitals, one of them's kind of going up and one of them's going to be spinning down, down. Okay, so that's really what the quantum numbers are. That's all I think you really need to know for the MCAT. It's a pretty good conceptual rundown. And they're really just the 4 different qualities, and remember that they're already baked into your electron configuration. The principal quantum number tells you the energy levels, and the other 2 quantum numbers are telling you which specific orbital they're in, and finally the spin. Okay, now I want to actually practice writing electron configurations. So let's do a little bit of practice. I'm going to go through these kind of quickly, but feel free to, of course, pause the video. Definitely recommend trying them before I kind of get started. So we're going to start with neon. So let's find neon on the periodic table. So this is how I do electron configurations. If I kind of almost think about it sequentially, one element in time, right? So if I were doing the electron configuration of hydrogen, the very first orbital, it would just be a 1s1. And then when we get to helium, right, it becomes 1s2 because we put another electron in the 1s. Then we get to lithium, becomes 1s2, 2s1, and so on. So by the time I get to boron, boron's going to be 1s2, 2s2, and then it's going to have the first electron in the p orbital. And then I need to add 5 more electrons to get to neon. 1, 2, 3, 4, 5. So that means neon is going to be 1s2, 2s2, 2p6. Okay. And remember, I just want to point out again, because I do feel like conceptually it's really good to kind of remind yourself this 2p6, it's not like we have 6 electrons in a p orbital, right? We actually have 3 p orbitals, the px, py, pz, with 2 electrons each. Okay. Um, so now let's try manganese, which is right here in the periodic table. It's element number 25. And so kind of going by our periodic table, we've got this hydrogen helium is going to be our 1s2. Lithium beryllium is our 2s2. Then we've got all of these atoms are going to become our 2p6, 3s2, 3p6, 4s2, and then finally we're in the D block. So this is actually called the D block of the periodic table, and that's because these elements kind of finish their electron configurations with the d orbitals. And the first row of the D block obviously has kind of the first electrons in d orbitals at all. And so manganese is going to have 5 electrons in its d orbital. And so it's going to be 1, 2, 3, 4, 5, and that becomes 3d5. Now you might be wondering, wait, why did I just write 3? And yeah, that's pretty weird, right? Let me finish kind of moving it down over here. Oops. 3p6, 4s2, and then finally, here's the weirdness, we've got 3d5 at the end. So why 3 and not 4? And to be honest, yeah, it's kind of complicated. But basically, the short answer is that the 3d orbitals, it really is a 3d orbital. So notice that as we move across the periodic table, we kind of add a new flavor of orbitals. So for the very first row, which only contains hydrogen and helium, we only have the s orbitals. The second row, you actually add the p orbitals now when you get to like boron, carbon, nitrogen, etc. Then that third row, what we should have done is we should have had s orbitals, d orbitals like right here. So there should be d orbitals here, and then our p orbitals. So we should have actually added in the d orbitals for the third row of the periodic table. But for whatever reason, it turns out that those d orbitals, they do exist, that they are there, but the atoms don't use them. They don't actually put their electrons in them yet. And I think that has something to do with the fact that those d orbitals are actually higher in energy than the s and the p. So the electrons never make it, like never have a chance to actually get into them. And what we will see, though, kind of later on in this series, and definitely in OChem, we'll see that these elements, so like aluminum through chlorine, empty d orbitals, they actually do have the ability to use those d orbitals in bonding. And so sometimes they'll receive electrons into those orbitals. That's looking way ahead. But anyway, so the 3d orbital, yeah, it actually is really, it was there all along. For example, it was there for sulfur and chlorine and stuff too. They were just empty until you get to the actual fourth row. And that's because those d orbitals are higher in energy. For your MCAT purposes, though, and honestly for most undergraduate classes, all you really need to know, or kind of like the bottom line here, is that the d orbitals kind of lag behind in number from the s and the p. So if you've got like a 4s, 4p, you're going to have a 3d, or 5s, 5p, you're going to have a 4d orbital. They kind of lag behind in number. All right, let's give our last example a try. And so for this example, we've got a ion. Actually, we've got a cation, which means that the aluminum is positive, and therefore it must be missing an electron. And I know that because we look at aluminum, right? It's right here on the periodic table, has 13 protons because that's its atomic number. And so normally it would have 13 electrons because that would make it neutral. But if it lost an electron, so if it had 12 electrons, then it would be +1 because there'd be kind of an extra protons worth of charge, making it positive. And so if it has the same number of electrons as an element with 12, that means this aluminum cation is going to have the same electron configuration as magnesium. Hopefully that makes sense. And so we're really going to be doing the electron configuration of magnesium. So let's kind of do this in the same way, where we've got the 1s2. Here's our 2s2, 2p6, and then we're going to end with our 3s2. That'll be the final answer. 1s2, 2p, or 2s2, 2p6. All right, video's already getting kind of long, so I think I'm going to kind of stop it here. And I hope this has kind of cleared up electron configurations. And most of all, I really hope you're feeling good about like what the electron orbitals are and kind of have a physical intuition for those. Oh, and that does remind me, we kind of started this by saying, reminding ourselves of the question of the last video, which is kind of what's the difference between the electron shell and electron orbitals? And now we can really fully answer that. So kind of the way that I like to think about it is the shells contain all the orbitals with the same principal quantum number. So for example, when we were looking at carbon before, its second shell had combined both its s orbitals and its p orbitals. So the 2s and the 2p orbitals, they have the same quantum number, so they're roughly the same energy. Therefore, they kind of get lumped together in the same shell. And that's why it's called the valence shell, because since those electrons all have the same energy and they're the outermost orbitals, they can kind of all participate in bonding and stuff. So that's kind of where the number of electrons in shells come from. Hope that kind of clears that up. All right, I'm going to stop there, and I'll see you in the next video.